So much of our world is run by code. But how do we actually trust it? Well, today we're going to dive into a really powerful blueprint for building that trust. It's a framework called Cove V1, and it's all about making complex systems provably reliable. I mean, think about it. This is the central question, right? Everything, our cars, our money, it's all becoming more and more automated. So how do we actually prove that a system is going to do what it says it'll do? How can we, bake that trust right into the code from the very beginning? And this isn't some future problem. It's happening right now. You've got self-driving cars, financial trading bots, autonomous drones. For this explainer, let's kind of latch on to that last one, a delivery drone. Imagine this thing. It's got thousands of rules programmed into it. But how can one be 100% sure that those rules will stop it from, say, making a really, really bad mistake? Okay, so here's the game plan for how we're going to break this all down. We'll start with the basic anatomy of any governed system. Then we'll get into this fascinating question of how safe is safe enough. After that, we'll see how these systems can connect to each other without losing that trust. And finally, we'll talk about this idea of a solemn promise that every trustworthy system has to make. So to even start building something you can trust, you first need a simple language to talk about it. And what's really elegant about the Cove V1 framework is that it argues any system, I don't care how complicated, it really just boils down to three essential ingredients. Okay, ingredient number one, the state space, which is just called X. Now, what is that? It's basically the set of every single possible situation the system could find itself in. So for our drone, right, a single state is like one snapshot in time. Here's its GPS, here's its battery level, here's whether it's holding a package. The state space, that's the whole photo album, every possible picture. All right, number two is the violation functional, or V. And honestly, the best way to picture this is as a built-in risk meter. It looks at every single one of those snapshots in our photo album and assigns it a risk score. A score of 0? Perfect. We're totally safe. But let's say the drone's battery is getting dangerously low, or it's drifting towards a no-fly zone. Well, that score starts to climb, basically shouting, danger. And finally, ingredient number 3, the receipt-verifier, or RV. Think of this as the ultimate no-nonsense gatekeeper. Its job is to look at any proposed move, from one state to another, and give a super simple final verdict, accept or reject. That's it. The drone wants to fly from point A to point B, the RV checks the plan against the rulebook. If it's good, boom, accept. If not, reject. It's totally black and white. So you take those three things, all your possible states, that risk meter, and the strict gatekeeper, and you bundle them together. And that package, that's what we call a Caja object. You can think of it as the fundamental atom, right? It's the basic building block for absolutely everything we're going to build with this framework. Okay, so we have our building block, this COH object. The next obvious question is, what does it actually mean for one of these things to be safe? Well, what's interesting is the framework gives us two different ways to think about it. Two, let's call them flavors of safety. So on one hand, you've got what's called zero-set admissibility. This is basically the absolute perfection mode. The system is only considered safe if that risk score is exactly 0, period. Any tiny bit of risk and it's a no-go. But then, on the other hand, there's bounded tube admissibility. This is the more, good enough or pragmatic approach. It says, hey, the system is safe as long as the risk score stays below some limit we all agree on beforehand. It gives you a little bit of wiggle room, a level of risk that's managed, and, crucially, predictable. Now, having these individual building blocks is cool and all, but the real magic, the really powerful part, is when we start connecting them together. This is how you go from one simple set of rules to these huge, complex, multi-layered systems that you can still trust, all the way down. I mean, just try to picture the raw data coming off our drone. It's like a fire hose, right? It's just a constant stream of information. We're talking hundreds of tiny little state changes every single minute, and each one is getting checked and stamped, approved by that internal gatekeeper. It's a lot. It's incredibly complex. But then you look at your phone, and what do you see? None of that complexity. You just see a nice, clean, simple summary, dispatched, in transit, delivered. So here's the billion-dollar question. How do you know that simple summary is actually telling you the truth about that super complex reality happening in the background? This is where this amazing concept called a comorphism comes into play. Just think of it as a mathematically guaranteed truthful translator. It's a bridge. It creates this formal link between the complicated drone system on one side and the simple tracking app on the other. And it guarantees that the simple view is a faithful summary. It proves that in transit means what you think it means, without you ever needing to check all those hundreds of little flight adjustments. Okay, this next point is really, really important. It's a critical distinction to make. See, it's one thing for a system to follow its own internal rulebook perfectly, but it's a completely different thing for those rules to actually lead to a good, safe outcome in the real world. And the framework is really smart about this. It separates these two ideas. You have legality, which is all about internal consistency. The question is simple. Did the system follow its own rules? That's the gatekeeper's job. But then you have soundness. And soundness asks a much bigger, more important question. Okay, great, you followed the rules, but do those rules actually stop the drone from flying into a building or from running out of juice over a lake? See the difference? So how do we solve that? With something called a soundness contract. Every single co-object has to make one. It's its public promise to the world. It's a clear statement in plain English that says, hey, I guarantee that if my rules are followed, this specific safe thing will happen. And that is huge because it means we're not just trusting lines of code anymore. We can actually read and audit the promise that the code is making. All right, let's zoom out for a second and look at the big picture here. We've seen the basic atoms. We've talked about how they define safety. We've seen how they connect together. So what does this whole blueprint for trust actually give us at the end of the day? This might sound a little strange, but what's so powerful about CoV1 is actually what it leaves out. I mean, look at this list. The core blueprint deliberately, on purpose, ignores all the messy implementation stuff. Specific hashing algorithms, JSON, network protocols. It doesn't care about any of that. All it focuses on is the pure abstract logic of the rules themselves. And that is not a bug, it's a feature. In fact, it's the whole point. By separating the timeless logic, the what are the rules, from the nitty-gritty tech details, CoV1 becomes this universal blueprint. You could build a system with it using today's tech, or the tech we'll have in 10 years. It doesn't matter, because those core principles of trust are kept clean, separate, and pristine. And when you get right down to it, this whole incredibly powerful framework can be boiled down to this one, admittedly pretty dense sentence. But we know all the parts now, right? The objects, those are our systems, like the drone. And each one is just a collection of its possible states. It's violation functional, that's the risk score, and it's deterministic legality predicate, which is just a fancy way of saying our strict gatekeeper. That's the whole thing. It's an entire universe built on this incredibly simple but powerful foundation of verifiable logic. So you see, what we're looking at here is so much more than just a specific technology. It's really a new way to think about building things we can actually rely on. It gives us a shared language to define rules, a way to measure risk, and a method for putting complex systems together with real, provable confidence, which really just leaves one last question for you. Now that you have the blueprint, what kind of system would you build?